So we want to factor the bottom here just as a good way of starting out, because if something ends up canceling,
life just gets infinitely easier.
Yeah, so what multiplies to get -6? That will give me a -1 when I add it together.
-3 plus 2.
-3 and plus 2. Now, if we're finding the intercepts, to find the x-intercept, we set the top equal to 0.
Yes. And when you set the top equal to 0, you're going to get a 1? Like 1?
Yes.
Okay.
To get the
Rock
y-intercept, we plug in 0 everywhere that there is an x.
Hey, that's even easier because I know how to do that. That's going to give me -1 over -3 and times -2.
Times positive
-3
2.
times positive 2, yeah.
Which
that's what I
is
said.
-1. You can use either one of these situations to plug it in. But keep in mind that anytime you do that, like the x's are all going to go away because there's 0, and so we should end up with whatever these numbers out at the end are. -1 over -6, which is a positive 1/6.
That is amazing.
And now the asymptotes. How about some vertical asymptotes?
Vertical asymptotes are going to occur where you get a 0 in the old denominator.
So where does x minus 3 equal 0, and where does x plus 2 equal 0?
-3 and plus 2.
No, at positive 3 and -2.
That's what I said.
That's not what you said.
That's what I said.
Horizontal asymptote.
Hey, guess where the horizontal asymptote is?
If the degree on top is less than the degree on bottom, it should be at y equals 0.
Big fat 0.
One way you can check is if you start trying to divide x squared into x, it doesn't go.
At all.
At all. So that's y equals 0. What else? Use limits to describe the behavior at the vertical asymptotes.
Ugh. Well, there's 2 vertical asymptotes, which means we're going to have 4 limits.
Yeah. So as x approaches, let's go from left to right. As x approaches -2 from the negative direction, you know, it might be helpful for us to have the graph to do this.
-2 from the left is going to go towards -infinity.
Well, I was going to actually draw the graph.
So I didn't cheat at all.
What do we have? We have vertical asymptotes.
-2 and 3. Little
at
v
positive 3
positive
and
3.
-2.
That's right. Never a truer word spoken.
Y equals 0.
This is taking shape here. I like it.
X-intercept at x equals 1.
Yep.
And y equals 1/6. And so what's going to happen here in the middle is it's going to look kind of like a cubic function in the middle.
And do your best in here. It can be really hard to string all those guys together, but it's going to look something-ish.
And if this is going up towards infinity, then it should be down here for the left side.
Shut the front door.
If it's down here and then it should be up here.
Just like all the other problems that look like this?
Yeah, exactly.
Get out of town.
Yeah, okay. So now, as we go -2 from the negative direction, so as we approach this first vertical asymptote from the negative direction, it's going towards -infinity.
Did you change your ink? You did. Okay,
I did.
Good job. And as we go towards -2 from the right-hand side now, that means let your eyeballs follow the graph from the positive side.
So this is in the middle. As we go towards -2, we end up going towards positive infinity. And then limit as x approaches.
3 from the left. It's exactly what we did on the previous identical spot.
3 from the left, it's going down.
-infinity. And 3 from the right. Totes posies.
Positive infinity.
Oh, yeah, that's what I just said.
Okay, and then analyze.
Well, analyzing, remember, is all the
kinds
GUIs.
of stuff, like
so
domain.
Domain. Well, guess what 2 numbers we can't have in our domain?
-2 and 3.
The those vertical asymptotes, those places in the denominator where we get a 0.
So we can go from -infinity to -2, and we can go from -2 to 3, and we can go from 3 to infinity, but at -2 and 3, we're not equal to.
Can't
so
have
we've got
those. And
parentheses.
please make sure that parentheses are everywhere here. We cannot play the guessing game on this. If we guess, you're wrong.
Yeah. If we have to guess between it being a parentheses or a bracket, we're just not going to. We're going to count it wrong. Range. The only issue is that at y equals 0, but wait, here in the middle we do have some values for...
It crosses right through there. Like,
So
we've
we're
got a
actually
value.
okay.
Yeah, we're good.
Any y value we want to, we could get an answer for because
right.
of there in the middle at crossing the horizontal asymptote.
Perfect.
Let's see. What's after
Domain range.
Continuity.
We are not continuous, and the reason we're not continuous is because we have a vertical asymptote. So anytime that you get a vertical asymptote, your graph automatically becomes a discontinuous.
Discontinuous.
Discontinuous
Do you
graph.
not know what the word is?
What are you writing there?
Discontinuity
Okay.
at x equals
3 and 2.
2 and 3.
Yes, that's what I said. I feel like your handwriting has suddenly gone
Increasing,
haywire.
decreasing, and constant.
Wow, this is going to be a really involved part because what we want to be able to do is tell where this y values are falling, where they are constant, and where they're increasing. Well, we're decreasing y values from negative infinity all the way up to an x value of -2, and you can tell that because all the y coordinates are getting smaller.
Right. And then, once we get past that asymptote at -2, I just didn't like the way I wrote that. That was right. I just thought it looked a little...
And then if we look again...
From -2 now... Oh, wait, we're still going down.
We're still going down. So from -2 to 3 now, we are also decreasing y values. Son of a gun. We are also decreasing again from 3 to infinity. That's just crazy.
Yeah, so we're basically decreasing on our domain.
Yeah. Now, it looks like on there's some arrows pointed up, but as you move from left to right across the graph, all the y values are falling down.
Yes, they are. Symmetry. I feel like this could be symmetric across the y-axis.
But it isn't because it doesn't cross through the origin.
Oh, you're right. No, yeah, I'm sorry. No, it's not symmetric.
It looks it though. It does look it.
It looks like, there's some kind of pattern going on.
Right.
But there's not.
If it were to go through the origin, we could quite possibly have a pattern.
Yeah, bounded or not bounded or partially bounded
it's unbounded.
It's unbounded.
There's no floor or ceiling that our graph can't break through. It's that strong.
Okay, extrema. There's not any maxes or mins.
Correct, because now you might look in these corners for max or min, but the y values are continually changing. They're not approaching a specific height or specific bottom, so there's no extrema.
Yeah, and next we would normally talk about our asymptotes, but I figured we already wrote them over here, so we don't really need to write them again.
No.
So our end behavior limits as the limit of x approaches -infinity of f of x. As we go to the left on our graph, we are getting closer and closer to 0. And also as we go
to the right, it's the same thing.
Right. There we go. That's everything. Hi. Find the intercepts, analyze, and draw a graph of the rational function.
Which we have been practicing actually this whole time.
We absolutely have. And until you get used to these, if you need to take a look at what something is in the calculator as you're doing it, that's okay. Just make sure you're making connections between what you're seeing on the calculator and what you're actually doing as far as the math goes here. So
because you're going to have to be able to reproduce some of these with a fairly accurate sketch on a test without a calculator.
It's quite possible.
Quite indeed.
Okay, so let's start with the intercepts. The x-intercepts you find by setting the top of the function equal to 0. So 2x squared minus 2, I'd add the 2 over to start off and get 2x squared equals +2.
Hey, this looks like something we might actually be able to work with here.
Divide by 2, we get 1. Square root both sides.
Plus and minus 1.
That is correct.
Yes.
So we have x-intercepts at x equals + and -1. Don't forget about the negative.
Always important.
Yeah,
negative.
Yeah, definitely. Y-intercepts. Remember we talked about that if we just think about if these x squareds go away, our y-intercept should be -2 over -4, which simplifies to be 1/2. But if you are unsure there, just remember you can plug in and find f of 0, and if you do, you get 1/2.
And f of 0 meaning everywhere you see an x, a 0 takes its place.
Yes. Analyze. So that's...
we didn't analyze and draw. We may need to draw first.
Okay, well, Well, let's go ahead and find the vertical and horizontal asymptotes.
Okay, rock on.
So on the bottom here, if I set this equal to 0, I should factor x squared. No, I don't have to.
You don't have to on this one, but you could because it is a difference of squares.
Right, so that would give us x plus 2 and x minus 2.
And if you didn't do that and you just move the 4 over, you'd have x squared equals positive 4.
And either way, we're going to end up with x being positive and negative 2.
That is correct.
So that's where our vertical asymptotes are. And then our horizontal asymptote, if we have one.
Ooh, we do have one because the degree on the top is the exact same as the degree on the bottom.
So it's almost as though like we're canceling the x squareds out. We're not literally doing it, but it's kind of like we're canceling out the x squareds. We're ignoring the negative 2 and the negative 4. So we get 2 over 1, which is 2. So that's y equals 2. Now I think we should have a pretty good idea of what this looks like.
I feel like pretty good at this point in time. Pretty good.
Okay, let me change to a different color. How about pink?
Yeah, now let's put in some asymptotes.
Okay, positive and negative 2.
Yeah. Wow, that asymptote, he walks like a sailor. Oh boy.
Y equals 2 is our horizontal asymptote.
Use your mind and pretend those are all 90-degree angles.
Hey, they're not that bad.
Okay.
The y-intercept is at 1/2, so right here at
there.
1/2.
Yep.
We have x-intercepts at 1 and negative 1.
Yep.
So this is going to look a little different than the ones we've been doing recently, because if you follow this through, like if this is where I'm going through the y-axis, this is going to look kind of like a parabola facing down.
Right, upside downy. And the reason we know that is because we've got to have something going on in there, and nothing goes up. I mean, we've got a high point at 1/2.
Yeah, that's what it looks like. And so now our graph should be at the top left and at the top right, because if I am headed toward this asymptote, headed down towards negative infinity, I should be back up at positive infinity here. Is that what the graph shows?
I believe that is correct. I'm just going to double check
just
these.
double check real quick. Yep, that's
what the
what it
graph
looks
shows.
like.
Yep.
And if we weren't sure, we could plug in like 3, for example.
3 and negative 3.
Yeah, 3 and negative 3, and then we'd know for sure where to draw the rest of our graph. So this is 18 minus 2, which is 16 over 5. That's a number that is bigger
than
than
a half.
3
Bigger than 2.
3.5, 3.2. So this would indeed be up here. And then we could check negative 3 and we'd find that this is in fact up here. Now that we have that, let's analyze.
Yes, let's analyze.
Let's analyze.
Let's analyze.
How do you feel about this graph?
I feel
is that not the
like
analyzation
this
that we're doing?
graph has reaffirmed my positive emotions.
Okay. Domain. We have 2 problems. We have
I feel like you
negative
didn't
2 and positive
positively
2.
reaffirm me with the course of the conversation.
That's not really what we're doing here. I'm not certified to offer you that. I'm only certified to teach math.
It's a good thing.
Negative 2 and positive 2, those are our 2 issues. So they're what is excluded from our domain. Our range here.
Now pay attention on range because not every value of y gets used.
Because if we're following values from negative infinity up to positive infinity, we really need to actually limit it from here, which is, we said 1/2, if that
1/2.
really is the maximum.
I feel like it is because according to our graph here, but I'll double check.
Yeah, let's double
And
check.
so this is an instance also where on your calculator you would just make sure that that maximum at that location is what it says it is.
And so he's going to analyze graph or second calculate if you're on an 84, and then doing lower bound, upper bound.
It says
Yeah,
1/2, 0.5.
So that means that we're going from negative infinity to 1/2. And then our graph picks up again
At the 2.
at the, yeah, and actually I'm so sorry, but that's a bracket because we said it could equal 1/2. See how I erased that so nicely?
There's no...
It can equal 1/2. It
Yes,
is 1/2
it is 1/2
right there
right
at 0. And then now we would pick back up, and it's not equal to at 2 because we've got an asymptote. It gets really close to 2, but never touches it. then it keeps going to infinity.
Yep.
That's kind of a weird range.
That is a weird range, but it works.
Okay, continuity.
Continuity means that you can draw your graph completely 100% prettily from left to right without picking up your pencil.
Yes, so in this case, this would not be continuous, and more specifically, we have discontinuities.
Whoa, plural.
Yeah, I went there.
Wow, that's
X
impressive.
equals -2 and +2.
Remember, we said this earlier, anytime you have a vertical asymptote, you're going to have a discontinuity.
Yes, increasing, decreasing, or constant. So
Ooh,
right
this is
here,
a lot of writing on this one, I think.
right here we're increasing,
Yes.
and then right here up to our max we're increasing. Then after our max we start decreasing again. So if we had not yet found out what that maximum was, we would have to do it right
We got
now.
it. We got to say.
So starting with increasing, I'm just going to abbreviate that.
Yeah, ink.
Inc. So we're increasing from -infinity until we get to our first asymptote,
Right?
and then from our asymptote until we get to the x value
The x
of
value.
that max.
That's the important part. Is we're looking at the x values where these y values increase.
Right, and so we would say that's at 0. And you could put a bracket around 0 if you were so inclined.
You could. You could.
But you don't have to.
In mathematicians, we'll discuss whether or not that 0 is included, but we're comfortable with that,
Yeah,
right?
we're comfortable either way. And then from 0 to +2, and from +2 to infinity. And we leave out the -2 and the +2 because the graph is doing nothing at those points.
Nothing at all, so we can't include them.
Yes. What's after increasing and decreasing and stuff?
Asymptotes, which we've noticed. We've already
How
determined all
about,
that. What about in behavior in behavior with limits?
well, that's usually a lot farther down.
Oh,
What about symmetry?
symmetry. This appears to have some symmetry.
Yeah,
would
I
say.
think it's symmetry across the y-axis.
I would say so as well.
And so we can check that really quick by saying, hey, if I plug in a negative x into my function, what happens? And hopefully we pretty quickly, since we've been practicing this, we'll see that, hey, those negatives get squared away, so I end up with exactly what I started with.
Right back to the starting spots.
Which does mean that this is an even function, so this is symmetry across the y-axis.
Symmetry across y-axis is usually pretty easy to see because you could just take your graph and fold it, and
They could be tricky though
They
and
could
make
be.
it look close to
They could.
it.
We had one just a few slides ago that was
Yeah.
close but not quite.
Yeah.
So
Is it bounded? No, it's
it
not.
is not bounded, although you might want to say it has got a ceiling and a floor. But if you say both of those, then you're not bounded.
Well, okay, we have a ceiling and a floor, but they're in the middle of the graph,
Right,
and that doesn't
right.
count.
Right.
I decided better spell this correctly.
Yeah. Spell
Okay.
it correctly. Let me see what
We
else.
have a max at
We don't have it. We have a local maximum.
a local maximum at 0, 1/2, and that's it. We have 1, 2, 3, 4, 5, 6, 7. You're all at home probably thinking, oh, well, our asymptotes up here, that was 1. So now
Yeah,
we're
we
at
had to talk about
behavior.
asymptotes. Asymptotes.
Asymptotes. In the behavior, using limits.
And it really is important that you write your limits correctly. I know we talked about this earlier, but
It's
when you get
super
into
important.
calculus next year, your teachers and your AP exam readers have to know what you're talking about, and there's only one way to write a limit.
The
So-
limit, as x approaches, whatever your values are, of f of x, in both directions, whether we're going to negative infinity or in positive infinity, we are approaching 2 with our graph, because that's our horizontal asymptote. That
All
should
right,
be all
I think
of them.
we've got the whole analyzation done.
And we graphed it, so we're good.
Fabulous. All right, so what we're going to do now is we're going to show you how to find all these in behavior items.
Should we find the in behavior asymptote real quick?
I mean, we can find an in behavior asymptote because your graph may or may not show that right off the bat. So there's a couple ways to do this. One is long division, but in this case, I think synthetic division is a little bit easier. If we look at that x minus 1 and set it equal to 0, we're going to have that x equals 1 is a 0 for this problem. So when I do my synthetic division, what am I going to have? Going to 1, -3, 3, and 1.
You said it was a 0, but you actually meant
What I
just
meant
that,
was
that's what solves
this is
it.
right. This is
Yeah.
what solves it. Yeah.
Okay.
So bring your 1 down, multiply and add, multiply and add, multiply and add. And we went from a third degree equation to a second degree. So basically what I have is x squared minus 2x plus 1 plus
Remainder.
the remainder, which is 2 over x minus 1. Okay?
But for in behavior asymptote, we don't care about that at the end.
We don't care about that guy. We just want this guy right here. So our in behavior asymptote for this particular problem is actually going to be a parabola.
Find the intercepts, analyze, and draw the graph of the rational function. So this is what we've been doing. But whenever we start going here, like we want to find the intercept, so we start with the x-intercept. On top here, if you set this equal to 0, you may have some issues with solving that.
-0.259.
Don't get ahead of. I didn't even ask for it.
Sorry.
The x-intercept, find it on your calculator. Graph this and find it. So what did you say it was?
I got -0.259.
Okay, so that's our x-intercept. Because we couldn't factor it, we might as well just graph it and use the decimal.
Yep.
But that's a last resort. Keep that in mind. Y-intercept. Everywhere the x is, I put a 0, which is going to leave me over here with
1 over -1.
Yeah, 1 over -1, because everything else is going to cancel out, which means that y equals -1 is our y-intercept.
That's what it looks like on the graph too.
Analyze. So we've already got our graph up because we had to have it for the x-intercept. Our domain, well, we know there's going to be a vertical asymptote at x equals 1, so our domain is everything except for that, right?
You got it.
How about that range?
How about that range? Well, basically, every value of y gets covered because of the...
Does it really?
Yeah, it actually
Oh,
does
see?
because of the left-hand side
Oh yeah,
of the
because the left-hand
asymptote.
side, that looks basically like a cubic function.
Yeah, so if you remember to the previous problem when we originally saw this graph, it shot straight up and shot straight down. So
Yeah.
we got everything.
So would this be considered continuous?
This would not be a continuous function because you have a vertical asymptote at 1.
Right.
So anytime you've got that vertical asymptote, there goes your continuity
So
right out the old
discontinuity
window.
at x equals 1. And then symmetry.
Symmetry, pretty
Not-
much no
no
symmetry. Bounded or unbounded on its domain, off its domain, it's bounded, not at all.
I was like about to say it is unbounded.
It isn't unbounded. There's no floor or ceiling that the graph does not break through at some point.
Right. Max, min,
It does have a local max, or I'm sorry, it's got a local minimum
right there on the right side
And it's
where
on
it
the-
almost looks like a
on
parabola.
the right-hand side here. So I'll just find that real quick.
So you're going to
So
analyze
if you
graph.
go menu, analyze, and find the minimum because that's the shape that we're looking at.
or on
there.
an 84, do second trace to
Yep.
your calculate menu and then click minimum.
Yeah.
We want a left bound, right bound.
Yeah, left bound, right bound, and
That's not really working out for you, is it?
and it's starting to work
There
out
you
for
go.
me now. So
You can do it.
here.
No, you didn't do it.
Okay, hold on.
Okay,
Here,
here,
there we go.
and then
Hey, look
Oh,
at there.
that's pretty.
2, 3.
2, 3.
Works out great. So
And
we have
that's a minimum because
that's a minimum.
it's a valley,
it's at a valley, and it's a local minimum.
which local just means at that it dips down at that point. It's
Right.
not the farthest.
No, it's not
south
the
of
furthest. No,
points.
right. But
But
it's
it's a minimum.
there's a bounce there.
Okay, so
Increasing and decreasing behavior. So if we look for increasing behavior, since you're writing that first, we're actually going to go to the right-hand side of our minimum. So
Right.
we would go from 2 to infinity. Now, again, we would say you could include the 2 if you wanted,
right, you could if you wanted to.
or you cannot include it, as it were. They're both going to be acceptable for us.
Now we can go on decreasing from negative infinity until our asymptote, right?
Yes, which is at 1.
And then we can go from 1 until we get to our minimum, which is 2. And that's where it's increasing.
Right.
1, 2, 3, 4, 5, 6, 7. So in behaviors one, asymptotes. We haven't actually
we haven't
listed
said.
those out.
You're right.
Vertical
So,
asymptote at x equals
1.
1. And we don't actually have a horizontal asymptote. We don't really have a slant asymptote either.
Well,
I
we
guess
do have a slant asymptote. We've got that
but
in behavior asymptote.
Okay,
I
so
guess
that's
is,
what I guess we should call it.
an in behavior asymptote.
EBA, in behavior asymptote. It's a thing. Start the trend. So on the previous slide, we did the long division for this. X squared minus 2x plus 1.
I think that was correct. Yes.
Yeah, so that's our in behavior asymptote. Our in behavior itself,
With the limits now, and this is going to be what the y value approaches as x goes to infinity.
right.
So,
And if I like to start with negative infinity.
hey, that's fine with me. It sounds great. It's got a
So
good beat
as we
against to
go
it.
farther and farther left, what value are we approaching?
Positive infinity, because the graph is going further and further up into whatever.
Then as we're going to the right,
We are going to be going up all the way to whatever.
right, in the middle there we have some other issue, but on the far left and on the far right we are
They're both
going up
going-
to infinity.
Yep.
Let's draw this graph.
Let's look at that bad boy. So we know that it's going to cross the x-axis at negative 0.259, so it's
that's
just barely,
really, really close to 0.
just barely.
Y equals negative 1, we've got
Yep.
a point. We've got an asymptote here at 1.
Yep.
And then our other asymptote is y equals x squared minus 2x plus 1. Well, I know that that goes through 1. And so basically it's going to be a parabola that opens up.
Yeah.
Something kind of like
Yeah,
this.
something similar to that.
And so we are kind of using our idea of what we thought this looked like from,
Previous
Yeah.
slide.
well, and from the calculator. So
Right.
I would connect these, and they're going closer and closer to that.
Right.
And then does it do?
I think it's on the other side there. I think it's on the inside.
Really?
I thought. Isn't it going to be on the inside right there?
Oh, I guess so.
I'll double check it. X squared minus 2x plus 1.
And so the thing is, again, this is our in behavior. So I mean,
So even if it's off just a little
cross,
bit.
It can cross it as long as the in behavior is true.
Oh, it's just outside of that graph.
I just undid the other.
Yeah, sorry.
Okay, so it is on the outside. So it kind of follows this curve up
Right.
like this. And then it's inside on these two, right here.
Yep.
Okay, so there we go.
There you go. There's the graph. And just pointing out that, we don't know exactly where that parabola is. Now, if we were to graph it, we could find exactly. But the thing is, the rough sketch needs to look pretty good.
Yeah. So I just realized we haven't given them a code word for this section yet.
Code word.
What did you say it was going to be?
Code.
No.
Catatonic caterpillar.
Catatonic caterpillar.
Put that down in a motto. Answer the question. Don't tell your friends. Yahoo. Have a great day.
Yeah, you too.